Welcome to the third lecture of mixed signal design. We are discussing unit and our focus in this unit is on sampling circuit. So in the last class, we were looking at the dynamic analog circuits of sampling, like sampling switches. We looked at the options of a MOSFET switch, both as NMOS, PMOS, as well as a transmission gate. We looked at how we can using understanding that for a sampling circuit what we need is a switch and a storage device. There are two options of capacitor and an inductor, and the popular one is using a capacitor along with a switch. And in that regard, we also looked at MOSFET in detail. And one thing what we understood is the source and drain can exchange their roles. That is proved with the help of these two examples. And one more thing, what we conclude is, the concluding remarks were this: MOSFET can conduct current in either direction by just exchanging the role of source and drain. And another one is, when the switch is on, the output follows input, and when switch is off, the output will remain constant. That is what we want actually, and we will see how the switches will help in doing this function called as tracking function. Now, we finished the last class with this numerical, where you were asked to calculate minimum and maximum on resistance of this switch M1. Do you have some answers for this? If you have, can you please post it here in the chat box? So in order to solve this, you should know what is the on resistance of the MOSFET. So this is an NMOS switch. So it is 1 by mu n C ox W by L into VGS minus VT, where VG gate is connected to 3 volt. We can call it as VD minus input Vin minus VT. This is the R down is this. And now if you substitute the value of V, yeah, basically you were asked to find the minimum and maximum on resistance. So you will get two values. One is around. Did you get any answer for this? What is around max and around minimum? All right. So the minimum value what you'll get is 870 ohms, and maximum value what you will get is 1.11 kilo ohms. You can just try it out and let me know what you're getting. So V in, you can take 0.5 as 1 and 0 as the other value. With that, I hope you will get these two values as around. I hope you are listening to me. Oh, okay. Now how is it? All right. So please let me know if my voice is breaking in between. I don't know. Today there is a small issue in the internet. So please do let me know. All right. So if you are responding, if I'm not seeing, at least please put a message in our WhatsApp group so that I can see from there. All right. So welcome to the third lecture of mixed signal IC design. And in today's class, we will look at sampling switches in a little more detail, where we will look at the speed considerations of a sampling and hold circuit. Right. So to start with, so we'll name it as speed considerations. All right. So for that, what I'll do is I'll take a sampling circuit, the basic circuit of NMOS switch and a capacitor here. So this is V in and this is V out, and here we are applying the clock. Sometimes so the clock voltage usually it switches from 0 to VDD. So we'll also write the clock as VDD as well, right? Now, say I have a clock edge here. So this is a clock edge, and the clock is from 0 to VDD. Now, what I'm interested to know, say for example, my input voltage. Now, my input voltage is at some voltage called as VN naught, V naught. There's some DC voltage. Assume that there is some DC voltage at the input side, uh, and we want to know how the capacitor is going to get charged at the post edge of the clock. So we know that when there is a switching from 0 to VDD at this point, the MOSFET turns on, and as a result, there will be a current flow here. So what will happen is capacitor will start charging, and the capacitor will charge to the input voltage V naught. But it depends on again it depends on what is the value of V naught. As of now, I'm assuming that V naught is well below VDD minus VT, so that the output can also charge to that value. But we know that will not happen all of a sudden. If I have drawn this clock diagram like this, and say here I'm going to plot the output V out. Say V in the final value, or the V in naught value is somewhere here. Say this is the V in naught value, and at the edge of this clock, what happens is your output V out it is 0, but it will start charging because there is a capacitor. It will charge, and it will charge to this final value of V naught, and that will not happen, or that happens, or the value of V out, which I have marked in red here, becomes V naught only at a particular time, and that depends on that will strongly depend on the time constant of the circuit. So when I say time constant, it is actually the charging time constant, which is R into C. So we will see what is this R and what is this C, but definitely we can say that your output will not come to V naught all of a sudden. It will take some time. So that is where we want to identify what is meant by speed, or what is the speed consideration of a sampling circuit. So before going to that, let me just define what speed it is here, or at least in a sampling circuit, what does it mean by calling it as speed? So can I get some response from you? What do you understand by speed in this case? In the case of a sampling circuit, what do you understand by speed? Rate of sampling, and I'm asking with respect to this specific circuit, because I know that the input is a constant V in naught, and the output is charging, rate of charge of the capacitor, how fast it stores value. All right. Charging of capacitance. All right, yeah, that is correct. So to be very precise, what I can say is speed is basically the time required for the output voltage, so V out, to go from the minimum value or the zero value, initially it was 0, to the maximum input level when the switch turns on, right? So that time, how fast the output can actually go from 0 to the maximum input level when the switch is turned on, can be identified as the speed of the circuit, right? So I'll just write it over here. The time required for the output voltage, the time required for the output voltage, here it is, I'll call it as V out, to go from, or basically it is charging from charging from 0 to the maximum input level, 0 to the maximum input level. When this should happen, when the switch is on, so after the switch is turned on, this is the condition. So whenever the switch is on, how long it will take for this output to charge from the minimum value or the initial value to the maximum input value, right? Now, but we know for sure that the switch what we are talking here is not an ideal switch which will offer a zero resistance, rather which is a practical switch which is implemented with the help of this MOSFET device. So we can say that the output will definitely take a long time to become V in naught, or output will reach V in naught only at infinite time, I can say. And for that reason, again, if you ask me why the reason for the output is taking a long time to reach the maximum value is because of the time constant of the circuit. We look at the time constant and the accuracy of the circuit also very shortly. Since we know that it always depends on the time constant, it will take a long time to settle to the final value. What we do often is we consider that output is settled. We often consider that the output is settled when it is within certain error band. So now look at this. Look at this waveform here. You can see that this is actually some voltage. This is some voltage. I can mark it as some delta V, which can be considered as a small error voltage because the output did not reach the final value of the input, but it is very close to the final value, right? So we usually consider that the output is settled if the output is within certain error band. So in this case, we consider delta V as the error band. So what I'm telling here is, since V out takes a long time to charge up to the voltage of V in naught, what we consider that the output in this case is settled when the output reaches certain error band. Now that error band, depending on the precision requirement, we can decide. Anyway, we'll see. And that error band we call, in this case, we mark it as delta V. And this error band should be around the final value. It should not be a large error voltage. This should be in and around the final value. This should be around the final value. Right. Say for example, let me take one simple example. Say I'm telling the output is settling to 0.1% accuracy after some seconds. Say I'm just marking this time as TS, and I'm telling that now this output is actually settling to 0.1% accuracy. What is the meaning of this? Are you guys with me? So as the output is taking a long time to charge to the final voltage V in naught, we are considering that the output is settled if it reaches a specific band, error band within delta V. And I'm just taking one example here. If the output is settling to 0.1% of accuracy, say after some TS seconds, what is the meaning of that? Are you guys with me? Can I get some response in the chat? All right. So when I say that the output settles to 0.1%, let me write it over here. If output settles to 0.1%, yes, 0.1% accuracy at say some TS seconds, the meaning is yes, 0.1% of V naught. So how can I write that? This delta V by V naught is actually equal to this 0.1%, right? that error voltage is actually only 0.1% of the V naught, that can be considered as negligible. Or in that case, I can say that after this specific time of Ts seconds, after this Ts seconds, I can consider both the source voltage and drain voltage. Both voltages, drain voltages, can be considered as equal. Can be considered as equal. Right. So what I was telling is, when you use a switch and a capacitor, your capacitor will not reach the final value all of a sudden, because capacitor charges exponentially and it will take a long time. So what we generally do is we consider if the output is falling within a specific error band, that again depends on the accuracy specifications. So if it falls within that specific error band, we'll consider that the output or the source and drain are equal at equal voltage, right? Now, let me ask this question. Now we are talking about the speed of the circuit, or we can call this as the switching speed or the sampling speed. So say now this switching speed. So can you tell me what are the factors on which the switching speed depends upon? If you look at the circuit, on what all factors whether this switching speed will be depending? What are the two main factors that that decides the speed, the switching speed of the circuit? Can I get your response in the chat? Error percentage, yeah. Error. My question is, why are you having an error? Why are you getting an error? So, what are the two primary factors from the circuit itself? Yes, R and C values, right? The resistor and the capacitor value. So, the switching speed is basically given by two factors. One is the R value. So when I say R, yeah, the time constant of the circuit, that is correct. The value of the capacitor, that is true. So when I say R, what is this R? This R is actually the on resistance of the switch. On resistance of the switch. And since this is on resistance, we'll mark it as R on. And it again depends on the type of switch that we use. If it is an NMOS switch, we'll write it as R on N or R on P, and so like that. This is one factor. Another factor is the value of the sampling capacitor. Value of the capacitor. So generally we call this capacitor as, we mark it as CH, the hold capacitor. So we write it as CH. So these are the two factors which the switching speed depends on. Now my next question is, what do you think? How? So generally what we are aiming at is to have a high speed, right? So now if my aim is to have a higher speed, or to achieve high speed, what do you think? In what way should be your R on and CH value? To achieve high speed, what should I do? If your RC time constant is large, it will take a long time to charge up to that value. So I should actually keep the value of R and C. Okay. Product of RC, yes. RC should be low, right? Yeah. Yeah, I hope Sriniket, you also understood that. Yeah, low. Yeah, RC value should be low. Now, to make RC low, what should I do with the MOSFET? So MOSFET is having an on resistance. Now, if I want to make the on resistance low, what should I do? What control as a circuit designer will have? Again, looking back at the expression what we have as the on resistance. So as a designer, what variable we have the control in order to have a low on resistance? Yeah, large aspect ratio, that is true. So one thing is, what we can do is we can have a large W by L value. So that will in turn reduce the on resistance, thereby increasing the switching speed. Or the second thing is, you can have actually a small value of small capacitor, CH. Now these are the things which we are stating. Now we should see how even these choices of MOSFET and capacitor will affect the sampling circuit even in the hold phase, because now they're actually looking at the sampling phase condition where when the clock is high, whether the output is getting sampled. Yeah, are you getting a sampled output? And now if you're getting a sampled output, uh, what is the final value of that sampled output depends on? It depends on the switching speed. Switching speed is basically the product of R and C. When I say R is the on resistance of the switch, and to make the switch resistance or the MOSFET resistance low, you should have a large W well. Along with that, you can also have a small value capacitor CH, right? Now, if you, yeah, so that is very clear. So now what we'll do is we'll make an effort to see what will happen in a NMOS switch, a PMOS switch, and why do we need to go for a transmission gate based switch, right? So what we do here is, if you look at the NMOS switch that we have looked even in the previous classes, NMOS switch, the on resistance value can be written as 1 by mu n Cox W by L into VDD minus Vin minus VT or VTH, whatever it is. This is the on resistance, right? Now, uh, the switching speed depends on R and C, but if you look at R, there is a problem here. The on resistance, there is a small difficulty. Can you observe that here from the equation of the on resistance? Here the resistance, what we have resistance that depends on mu and C of WL, which is the process constants, aspect ratio, threshold, VDD. Also, you can see that there is a dependency on the input voltage, right? So here the on resistance R on depends on the input level also. R on depends on the input level. All right. So now, if your R on, the input on resistance is depending on the input voltage, what will happen? What do you think? What will happen? What can happen? What is the problem if your switch resistance depends on input voltage? Yeah, it will be variable. Yes, very good. So you will not have a specific resistance. Rather, your resistance will be keep on varying, and which is something which is not actually what to say preferred. So why it is because can we have a plot of this on resistance here of this NMOS switch? So this is switch. This is the input. So as we know that the on resistance of the switch, I'll call this as R on of N, as it depends on the input voltage V in. Can you tell me how will be the plot? So what we know here is as we keep on varying the input voltage, your on resistance will vary. So let us start with at V in equal to 0. What will happen at V in equal to 0? When you substitute V in equal to 0, your R on is equal to 1 by this specific, the constant value mu and Cox W by L into VD minus VTH. This is the resistance. So that will definitely give you some value. Maybe I'll mark it somewhere over here. This is the initial value. Now, because the V is 0, now what is happening? Your V is keep on increasing. Right? Now your V is variable, and if your V is keep on increasing, what will happen to your R on? Whether it will decrease or increase? So as V increases, denominator term will decrease. As a result, R on will actually increase, right? So what happens is R on will keep on increasing like this. And can you tell me at which specific point your R on becomes infinity? Yes. So as your input voltage reaches a specific value, say your Vin is equal to VDD minus VT, what will happen is this is your VDD minus VT point, and then your on resistance will become very, very high. Right. So this is the characteristics, or this is the on resistance variation of a NMOS switch. So you can see that the R on value sharply rise as Vin, this Vin value approaches VDD minus VT or VTH. Right. So now if you look at this, why is this happening? You look at a switch, why is this happening? This is gate. and say this is drain, this is source, because initially I'm assuming that there is a capacitor and there is no voltage across the capacitor, so I'm considering this as source. Now if I have actually connected a voltage, say a voltage is equal to V in, initially let me assume that the voltage is equal to VDD. What will happen? The capacitor will start charging, and this voltage, this node voltage, so as this so this is at a constant VDD, this is at VDD, now this is at 0, and this will actually keep on increasing, and it will try to reach a specific, it will charge up to VDD. But what will happen here, if this node voltage, so for the switch to be turned on, what I need is a VGS voltage of VTH, right? Now what I connected to gate voltage is some VDD, because the clock is high. I'm assuming that the clock is high, so I have a VDD voltage here. Now if this output node or the source node, if it charge and say the charge reaches up to VDD minus VT, what I have here is, to the gate I have VDD, to the source I have VDD minus VT. That means I have just one threshold voltage between VG and VS, or your VGS is only VTH. That means that the MOSFET will be turned on. That means since the output, as the output reaches VDD minus VT, till that value the MOSFET is on. But if the output try to charge beyond that, it cannot charge, because what will happen if it try to charge, the VGS value will fall, VGS will fall below VT, and this makes the transistor off, right? That means it will offer a huge resistance. So with that, we can say that an NMOS switch can charge only up to VDD minus VT. The same thing what we have seen here is also same. So as you keep on increasing your V in voltage, your on resistance will also increase, and maximum at VDD equal to at input voltage equal to VDD minus VT, your on resistance will become infinity, right? Now similar thing you can actually similar observation you can make with respect to a PMOS switch. We will see that. So before that, let me also tell you, now if you know that the on resistance is keep on increasing when you have an input voltage very close to VDD minus VT, it is not good to use that switch to that input voltage. Why do you think it is not good to use a switch up to that level? One second. Yeah. Are you guys with me? Hello. Yes. So what I was asking is, if you know that the on resistance will be very high if you apply an input voltage very close to VDD minus VT, it is very obvious that we should not try to apply a voltage very close to that, right? Because it will definitely give a large resistance that result in larger time constant, and that will result in lot many other like it is, in fact it is a non-linear. If you look at the resistance, the nature of the resistance, it will actually give you a non-linear resistance. So what typically is done is, we'll always try to restrict the range of the on resistance. So for example, say if the the on resistance variation, if I have this R on, and if I'm making this R on variation, if it is restricted to a specific range, say I'm restricting to a range of 4:1. I'll tell you what is this 4:1. So now you have the on resistance of the NMOS switch, right? And this can have two values. One is the on resistance for input voltage equal to 0, and the next one is on resistance for which input voltage is equal to maximum. Right. Now, I'm not looking at the maximum value, which is VDD minus VT. Rather, I'm just looking at what can be my maximum value if I restrict the ratio of on resistance, say from 4:1. Right. So, what I'm trying to say here is the R on, when you have the maximum input voltage, is equal to 4 times R on of V in equal to 0. This is the, if I'm restricting to this ratio, what is the maximum input voltage? I'm just trying to look at that, right? So how can you write the on resistance of the switch when your input is maximum? I can write it as 1 by mu n Cox W by L into VDD minus, this is V in maximum, minus Vt. This is the maximum on resistance. Now I am restricting that to this 4 times of R on. What is the on resistance when V in is equal to 0? It is equal to 1 by mu n Cox W by L into VDD minus Vt. This is my on resistance because I just substituted V in is equal to 0, right? So if I just cross multiply this, what I can do is I can actually cancel out these terms, mu and Cox W by L, and what I have left out is 1 by VDD minus V in max minus Vt is equal to 4 divided by VDD minus Vt. Or this can be further written as VDD minus Vt is equal to 4 times VDD minus 4 times V in max minus 4 times Vt. And if I solve this, I can get an expression for V in max, and here V in max will be equal to 3 by 4 into VDD minus Vt. Right. So what is the aim of doing this? What I was telling is, if you are trying to if your input voltage, if your maximum input voltage, if you are restricting to 3/4 of VDD minus VT, then your on resistance ratio is actually 1:4. So the whole idea is, say if you look at this plot here, this is V in and this is the on resistance maximum, and as we know that this is moving like this. This is VDD minus VT. So say this is R on, and we may go up to, say this is 4 R on, where your this is 0.75, 75% of this VDD minus VT. But then also in some technologies, say if this value is coming around VDD by 2 in some technologies, say approximately if this is coming to around VDD by 2, then this also will actually give you some kind of swing limitation, because whenever you have a supply voltage VDD, we will at least expect that your input voltage will go up to VDD or very close, a value very close to that, right? So your input, the maximum input voltage what you can apply is only up to VDD by 2. In some of the technologies, when you have the maximum value is 3/4 of VDD minus VT, right? So it all depends on technology also, but what the point here is, we always try to restrict the input voltage because keeping a large input voltage very close to VDD minus VT also will result in a huge nonlinear resistance, and it cannot be also kept very low, because for any circuit to work in a specific supply voltage, you should have a sufficient swing, right? So the underlying point is, if you use only an NMOS switch in this fashion, you will always have a swing limitation. So that is the takeaway from here. The limitation is your NMOS switch conducts only up to VDD minus VT. Second thing is, the on resistance is non-linear, as it depends on input signal and therefore we will definitely have some swing limitations. Is this clear? Can I get some response in the chat? Is this clear, the things what we discussed now? All right. Now, probably now you can think. So here, as I mentioned that V in max, the maximum voltage is only 3/4 of VD minus VT. So there are techniques actually that we will see towards the end of this unit. There are some techniques which we use um, in order to make this NMOS switch to conduct, and such techniques are called as bootstrapping techniques, where we will drive the gate voltage up to twice of VDD. That we'll see shortly. We will see towards the end of unit 1. We will see that that is one method called as bootstrapping, where we change this NMOS switch, or we can better utilize this NMOS switch. Anyway, before that, let us also look at this PMOS switch CARA. As in the case of a PMOS switch, you know that on resistance can be written as 1 by mu p Cox W by L into V minus mod VTP. So how I have written is the same expression, but in the case of PMOSFET, how we will write is VSG minus mod, this from the same current equation I have just written. So in this case, it is VSG SG, and let me draw a diagram over here. See, if this is the case, this is V in, this is V out, and this is VDD or the gate. Now, when I look at the VSG voltage, this is VSG voltage. VSG voltage should be actually positive, or VGS should be negative. So for VSG to be positive, I can, and this is not VDD. By the way, this will operate when the clock is low. So this is 0. So what is your VSG? VSG is nothing but V in. That is how the expression becomes this V in minus mod VTP. And this is the on resistance. And as similar to that of your NMOS switch, if you plot this PMOS switch CARA, if you plot the R1 of P, what we will know is, or can you tell me how will be the switch, how it will respond? In the case of NMOS switch, at VDD minus VT, the resistance became maximum. Now, similarly, at what voltage the resistance will become maximum in the case of a PMOS switch? Any guess? Can I get some response? Yes. So it will happen when your input voltage is equal to mod VTP, your PMOS switch will have an input infinite resistance. Otherwise, your resistance will actually reduce like this. So this is the response of a PMOS switch, right? So if you look at the response of NMOS switch, it is like this. For a PMOS switch, it is actually the other way. So, Anish, I didn't get the question. Minus of that means what? I'm looking at input voltages from 0 to a higher value. Are you asking a question, Anish? I didn't get the question. Then. Sorry, Anish, I'm not able to hear you. If you are responding, if you want, you can unmute, or else you can just type your comment. I can read it. Okay. Yeah, got it. Okay, so now, since your NMOS on resistance CARA is like this and PMOS is like this, now when you go for this, the combined switch, we call it as transmission gate switch. When you have this transmission gate switch, where you will combine both NMOS and PMOS together, where this is clock and this is clock bar. I'll just connect in this fashion. This is V in and this is V out. Now it is very clear that when you have both transmission gates, when you have both NMOS and PMOS switch together, the on resistance will be actually the equivalent on resistance of both, which is R on of P parallel to R on of N, right? These two will be parallel. The same equation will hold good there, because we have written what is the on resistance of both NMOS and PMOS switch. And if you look at the graph, the graph will be like this, something like this. This is input, this is the on resistance of the transmission gate. Now I'll mark one point here, which is mode VT, another point here, which is VDD minus VTN. So for an NMOS switch, NMOS switch will initially have all right. So for an NMOS switch, initially you will have 0, and then, sorry, not 0. At 0 you will have some on resistance, and that will increase like this. And for a PMOS switch, it is like almost like opposite. So in combination, what you will have will be something of this type, right? So I'll mark this as R1 of P, this as R1 of N, and this as R1 of the transmission gate. And as we have seen that there are the on resistance of NMOS switch and PMOS switch will go to a high value at some extreme voltages. Here is your transmission gate, which will actually give you a moderate on resistance across the voltage from 0 to quarter voltage VDD. Right. So, like compared to the PMOS switch and NMOS switch, transmission gate switch, or this is otherwise called as complementary switches. Complementary switch. This is used. And this is used whenever, or this will actually give you a larger, the advantage of this is larger voltage swing, because it have a larger range because of the parallel combination of both this NMOS and PMOS switch, right? But that is not the end of the discussion. We have to discuss more about this. What we'll do is we'll continue in the next class. So we'll wind up for today. And if you have any questions, you can please ask.